So as I mentioned now, we have Frances Leroux on board. She is a PhD candidate in electrochemistry-based digital twinning of lithium-ion batteries. Frances, are you with us?
Hi there, yes I am.
Fantastic. Frances, I'm going to be very honest with you. I'm not an academic. I do this talking and I listen to very smart people like you to help form my opinions. So I'm really excited to hear what you have to say. Over to you, and let's talk us through your presentation.
Cool, thanks so much for having me. I'm really excited to be able to share a little bit more about the in-depth role of simulations, etc. In EVs. So yeah, my talk is going to be based on the role of battery simulation in the localization of EVs in South Africa. So yeah, let's just jump straight into it. I just want to say this work is based on what I did for my master's. I just want to see here. Sorry, my slide didn't want to go to the next one. There we go. And I'm just going to do a brief introduction and then talk about modeling and simulation of lithium-ion batteries, and then how I feel that this plays a role in EVs in South Africa. So as I was saying, just a little bit of an introduction of myself. My name is Frances Leroux. I did my Master of Engineering at Nelson Mandela University, and my work was in collaboration with Uyilo e-mobility program. I'm sure many of you have heard them before. Also doing a lot of work in line with the localization of EVs in South Africa. And my master's work was titled Modeling and State of Health Prediction of Lithium-ion Batteries under Dynamic High Current Applications. By dynamic high current applications, I'm talking more in lines of power tools, those applications, but nevertheless, the work is always applicable to similar fields of battery applications. And so just because I focused on higher current applications, it doesn't mean that we can't apply what we've learned to EVs. And basically my main task was looking at commercially available battery simulation solutions. And I was modeling the cyclic aging of lithium-ion batteries to see how we could use the data generated by simulation for state of health algorithms. And I will touch a little bit more on state of health and battery state estimation. I'm going to give a brief overview of batteries, why we use them, and then show you a little bit of what I did in using commercially available softwares, and then touch a little bit more on simulation and all of that. So I'm currently, as was mentioned before, just a little additional bit of information. I've actually relocated. So I'm currently based in the Netherlands, and I'm focusing on electrochemistry-based digital twinning of lithium-ion batteries. So this differs from my master's work, where I focused more on commercially available software. I am now focusing more on the actual digital twinning and modeling of lithium-ion batteries, and I'm focusing on electrochemistry-based solutions. But if you don't know what that means, don't worry, because I will get into it soon. So just some important battery themes that I think it's really good to have an overall view of why we have batteries and how we should use them. And when we're utilizing lithium-ion batteries, one of the most important aspects that we know is that we want it to be safe, and we want to be able to ensure the lifespan of the battery. And people like me who research the more in-depth aspects of the batteries, we're trying to look how we can achieve this. So we want to not only make the battery safer, but also know how we can utilize them again and make it more environmentally friendly. So make our application of the batteries more environmentally friendly. And so if we just go on to our next step, it's basically, I would say, 3 important steps that we need to look at in order to achieve this. We need to understand the battery behavior by implementing it in battery models, which will allow us to visualize the behavior of the battery. And we can then apply this in battery management systems. So this is a very brief and quite a broad overview of a battery management system and the key functions that we find within a battery management system. So of course, just to also provide more details, within a battery, we obviously have many cells connected in series and parallel, depending on the amount of power which you require from your system. And so a battery management system is mainly used to monitor and control the operation of the battery. And why do we need to do this? Because we need to ensure that our battery is always operating within its safe operating zones, because there are obviously quite a few dangers which can be involved with the operation of lithium-ion batteries. And we need to ensure that we don't have any issues. For example, thermal runaway is one of the most common known errors or faults occurring within batteries. And in order to reduce this, we need to constantly monitor the temperature of the battery as well as the state of health of the battery. So within our battery management system, we've got 4 focus areas. We've got measurement, control, state calculation, and diagnosis. So measurement, as I just mentioned, would be the monitoring of the temperature, the voltage, and the current of the battery. Now, you may ask, but why do we need to constantly monitor the voltage and current? Why don't we just provide the power to the whatever we're using it for? If it's an electric truck, why don't we just provide the power to the drivetrain? The thing is that we constantly need to know the state of charge, maybe also in assisting with range anxiety, and as well as the state of health of the battery. Now, state of health is a really important factor for knowing the end of life of your battery that you're using in your vehicle. So most electric vehicles batteries only have or are only operated until they reach 80% of their state of health, and then they can be repurposed for other applications. And our state of health algorithms are essential in knowing when we've reached the stage, because when it's reached a certain level of state of health, we can no longer use it for a certain application because it can no longer safely provide the power and energy which we require from the system. So state of health and then state of charge are both essential, both for knowing how much further, of course, it's like having a fuel gauge, knowing how much further we can go with our battery, and as well, how much longer, how many more years do we have left in our battery. So then that having state estimation and measurement leads to the control and diagnosis of our battery. So control, I'm talking about battery control in terms of cell balancing, cell management. I'm not going to go into too much detail in terms of cell balancing, but you'd get different forms of cell balancing, and knowing and keeping the cells balanced is really important in ensuring the longevity of your battery. So making sure that your cells are constantly balanced will help your battery to last longer, and as well as prevent phenomena such as thermal runaway. And then we also have our diagnosis, which is error detection. And this goes hand in hand a little bit with our state calculations, because they can help warn us when there is an issue within the battery. So looking at modeling and simulation, now I'm going to go into the details. We get 2 types of battery models. And just to recap, why do we need these battery models? What is the point? The point is to help us get information without performing physical tests on the batteries, help us get more information so that we can build these algorithms which I just spoke about. So for our state of charge calculation, for our state of health calculation, we really need a lot of battery data, and it is not always that useful to collect all of this data by means of actual cycling tests. And this is where battery models really can be quite useful, because we can develop our algorithms based on the information which we get from our models instead of from actual battery testing, saving us a lot of time and money. So in the world of battery modeling research, there's kind of like 2 dominant types of models which we're looking at. That is our equivalent circuit models and electrochemical models. So as I've mentioned, I'm focusing on electrochemical models. So it's a little bit of a more complex model of the battery. But just to give us a small little comparison here, equivalent circuit models have a lower computational burden, but they do not consider the internal electrochemical behavior of the battery. So there's a lot of complex electrochemistry reactions happening within the battery, and they really do affect the behavior of the battery quite significantly. And an equivalent circuit model does not necessarily represent this behavior very well, but it is useful to use in state of charge indication. So when you're trying to understand the relationship between battery voltage and state of charge, an equivalent circuit model can be very useful. However, when you're trying to look at more complex development, such as state of health prediction and such, an equivalent circuit model just doesn't provide enough information about the operation of the battery. However, electrochemical models are much more computationally expensive, but they do consider the internal electrochemical behavior of the cells. And these are very good, as I mentioned now, for state of health estimation and also for the development of optimal charging strategies. There is some really interesting work going on, which could be really useful in the localization of EVs as well, in development of optimal charging strategies based on battery aging. And a researcher locally here has done some really good work in aging-aware charging. And I think this is all really tied in so deeply with modeling of batteries. And yeah, this world, it's just continuously developing, and we really still have so much work to do in terms of electrochemical models, but we are all people trying just to advance this field of modeling, because the models are really exceptionally useful when we want to implement accurate battery management systems. So I'm just going to focus a little bit now, not go as in depth. This is a little bit broader. And this is modeling for state of health prediction. This is the work that I covered in my master's. And I actually utilized Siemens SimCenter AIM-Sim. It's a software which is commercially available from Siemens. And I use their software for the generation of data in my master's work, and it played quite an important role within my research. As you can see here, I have a basic single cell model that I developed. It's just an electric circuit containing a voltmeter and a current source, and I was able to continuously charge and discharge a single electrochemistry cell model, which they have commercially available in their software, which I think is amazing. This is really useful in industry applications, in terms of training people, etc., because you are able to use electrochemical cell models, which they've already developed, and apply them within your own applications, and then you can analyze how the battery responds to the different applications. So this is exactly what I've done. I've utilized an electrochemistry cell model, which they made available, and designed a small circuit to illustrate the basic charge-discharge profile that a single cell would experience. And then I utilized all of this data to understand how the cell was aging over all of these cycles. And then I was able to use that within my state of health algorithm. Now, I'm not going to go too much in depth into the state of health algorithm, because I think it's not exactly the point that I'm trying to convey with this talk, but more and more trying to focus on the usefulness of modeling in industry. So, as I said, the battery aging data was then generated and utilized to train a machine learning algorithm. And Siemens SimCenter AIM-Sim, I also want to mention, doesn't only provide a electrochemical model, but they actually have an entire list of different lithium-ion models which they make available, as well as battery models. And I think that if you are in industry or you're in the field of trying to train someone, this could be really useful in terms of really understanding and conceptualizing how the battery is operating under the various applications which you would like to use it. So I just wanted to focus a little bit on the advantages and disadvantages of modeling in comparison to maybe actual battery testing. So a lot of people do develop algorithms based on charge and discharge or aging data, which they have generated themselves, but that does take a lot of time. So some of the advantages of modeling is that it allows one to understand the behavior of the cells under the various operating conditions. However, not all aging models represent the full electrochemical processes occurring within the cells. So even your complex electrochemical models do not always illustrate the full behavior. So as I mentioned earlier, there's really still a lot of work that needs to be done within this, and some models may represent electrochemical behavior in terms of certain aging aspects, but then not all. So we often refer to aging as linear and non-linear aging. There are some aspects which we refer to as linear, which is simpler to model. And then we have some complex aging mechanisms, which we're still struggling to model today. So although it allows one to understand the behavior, and it does allow you to generate relatively accurate control mechanisms, it's still not as accurate as we would like. However, by generating data using models instead of testing, we really are saving a lot of costs and time as well. And as I kind of said, we are looking a bit at this computational expense as well as accuracy. So we have a little bit of a play of when it comes to electrochemical models, equivalent circuit models, as well as battery testing. We really are trying to find the perfect relation in terms of computational expense and the accuracy. And as I mentioned, yeah, cyclic aging testing is quite resource intensive. And then just another aspect is, of course, that commercially available software can be quite costly. So if you are looking at using models which already exist and not developing your own models from the beginning, it can be quite costly. However, I think that this is kind of where it's going to be going in terms of battery modeling, because not every company has the time or the resources to develop their own electrochemical models from scratch, as well as the knowledge. It really takes a long time to understand and conceptualize all the behavior of the cells. So this is where using commercially available software can be quite useful. Now, I just want to look a little bit of battery modeling and the localization of EVs in South Africa. So I'm trying to link the concept of modeling and how it can help us. Just looking back, this is another battery model which I developed within Siemens. And this one contains various cells connected in series. So I basically modeled a 12-volt cell here instead of just a battery, instead of one single cell. And this allowed me to see how the battery as a whole responded to the various operating conditions. So the details of the electrical design are not really important, but I just wanted to illustrate what you could be able to do. And I'm going to get to a section now, which I'll show you some results. And then you can kind of just see how useful it is. And it really helps us to understand how battery circuits and battery management systems need to be designed, as well as how the cells need to be monitored, the cell balancing which needs to occur, the programming of a BMS, as well as state estimation. So when you would need to set up a model like this, it could really be quite a learning curve, because you would have to look at what are my operating parameters for the battery, what are my minimum voltages, what are my maximum voltages, what temperatures can my battery operate within. If each cell is at a slightly different temperature, how does that affect my response as a whole? And just various, what do different charge currents, what does that do to the battery? What do different discharge currents do to the battery? And all of these are things that we can learn simply by modeling a cell or a battery. So instead of applying all of this to some physical battery, which we would need to test in the lab, which also, of course, can raise different safety questions, we can do this all by building a relatively simple electric circuit on our laptops, and we're able to visualize all of the results. So this is a result from one of the battery simulations which I ran, and these are 4 different cells. So this result is from the setup which I showed in the previous slide. It's my 4 cells which are connected in series to make a 12-volt battery, and I've monitored the voltage of each individual cell, and all the cells are charged and discharged at the same current. This battery underwent quite a not crazy dynamic, like as intense as you would find in your electric vehicle, but a slightly dynamic charge discharge profile where I discharged the battery at quite a high current for a couple of seconds, then at a lower current for about a minute, and then even lower. So it just has a little bit of a varying discharge profile, and that allows us to see the response of the voltage of the battery. And as you can see, as soon as you're doing the orange line on there would be the current. So as soon as you're doing a relatively high discharge current, your voltage is dropping quite significantly, and then it almost does a little bit of a recovery profile. So this is a typical example of how you can utilize a simulation to understand the response of the battery. Now you see that we've got 4 cells, and they're different. They're represented by the blue lines, which each have slightly different. You've got the solid lines and the dotted lines, and you can see that my cells are dropping to different voltages. And this is because at this moment, each cell within this battery was considered to be at a different temperature, as well as a slightly different state of health. And you can see that this largely affects the response of the cells, which means that your management of the battery needs to be quite specific and accurate in order to prevent a cell from dropping to a voltage which is too low and experiencing thermal runaway or spikes in the temperature. So this is really important to understand and conceptualize that if I have a battery where my cells are not all at the same health, how does this affect the response of the battery as a whole? And some people may say, yes, but when you get a new battery, you've got cells and they're all new, so they're all healthy. This is not the case at all. No cell coming out of a manufacturer's factory has exactly the same state of health. You will always have a slight variance in the health and the available capacity of your cells within a battery. And thus it's really important to understand that your cells within a battery are always going to be reacting slightly differently. And this is where simulation can really play a helpful role, so that you can conceptualize and really plan for different responses within the battery. Now, I'm just going to sum up a little bit here. And just looking at battery simulation in South Africa, I really think that battery simulation within tertiary education can be quite a useful tool, especially within the future of EVs in South Africa. And I think that we are definitely headed there. It might not be immediate, but it is definitely in time to start to step up the knowledge of our younger generation, and just so that people generally can understand the operation of batteries. And I think this is where these modeling tools really can be quite handy. And it's also, of course, useful in the development of efficient battery management systems, and utilizing them for data generation, as I mentioned. And there's just a single line referring to charging stations. As I said, there's a lot of work being done in utilizing battery modeling for the development of aging-aware charging, which is a really interesting topic and could be really useful within our industry, especially in South Africa, and people having so much anxiety in relation to our grids and the demand which EVs might place on the grids. And finally, I just find that modeling could be quite a useful tool even within industry, when we are moving towards an industry where we are focused on EVs, and perhaps we might not be developing the batteries from scratch within South Africa. But I think that there is definitely going to be a requirement for employees to understand how the batteries are working. And I think that this is where modeling and simulation could really play a big role in generating some knowledge within the field. So yeah, that is pretty much a brief overview from my side. We can move on. If anybody has any questions for me, I'm happy to answer them.
Perfect. So Francis, I have a lot of questions here, and I'm going to acknowledge all the people who are giving me all these questions. They must be academics, because they're understanding understanding all your euphemisms or your questions. I'm gonna cherry pick one, but then I want to try and steer us a little bit more towards what consumers might benefit from your modeling, because I think that's what we need to focus on is what does work like what your work do for the average consumer, me on the street who wants to buy an EV. What does your kind of modeling do? How does it help me make sure that I'm buying the best EV that I can out there? So I'm going to touch on one technical question to have all our techies a little bit happy, and then I'm going to hand over to George because he's going to go on the consumer side. How does solid state batteries affect the outcome of simulation? And I'm picking on this one because I think consumers understand solid state batteries. The question comes on a lot. And do you see solid state batteries as the future of EV batteries?
If the question is with relation to solid state batteries, I'm not 100% sure what the question is implying to. What exactly do they mean by solid state batteries in relation?
So solid state batteries, does it affect the outcome of your simulation? Have you run any simulations on solid state batteries? And then just an opinion on, do you see solid state batteries as potentially the future of EVs?
I haven't specifically run too many experiments on solid state batteries. I've more been just focused in with one area, so I'm not sure that I can accurately answer this question. So
fair enough, no problem.
Sorry.
No problem. George, over to you.
Francis, that was fascinating. You know, I had to really concentrate there. You're a smart lady, and I think South Africa, has to benefit from the work you do. So thanks for that. But kind of like just in my own layman's terms, when thinking about the recycling of lithium-ion batteries, I often come under fire when it comes to naysayers, saying to me that your EV might be more efficient on the road, and you're at 80% efficiency versus 15% efficiency in an ICE vehicle, but your battery still has to be recycled, and then things are equal when it comes to fossil fuels and burning fossil fuels in these noisy ICE vehicles. So what does your research or reading show when it comes to recycling of lithium ion? Is it as bad as the fringe couch experts say it is?
Yeah, that's definitely an interesting question. I think that our focus needs to be more on repurposing of lithium-ion batteries initially before we start focusing on just the recycling of lithium. So in the beginning, when I spoke about our usage of batteries and making that quite efficient, I think that we should, once an EV battery reaches its end of life, which is generally considered once it reaches 80% of its full capacity. So once we get to that point, we can utilize the EV batteries for other applications before we even get to the point of recycling lithium-ion batteries. So I think it is definitely, I know that the physical recycling of lithium-ion batteries is quite intensive and a little bit expensive, maybe environmentally. But I think that if we focus our energy also on the repurposing of the batteries, we can get a little bit more out of the batteries before we have to reach that point of recycling. So I think a lot of people focus on, but recycling of lithium is really, it takes a lot and a lot of energy and is quite expensive in many ways. But I think that we forget to focus on the fact that before we get to that point, we can still utilize the batteries a second time.
Thank you, Francis. I think that's a very good point you make in terms of repurposing the batteries themselves, because that kind of brings down the cost of the impact to the environment. And a second question I had was, is degradation of lithium ion that bad in EVs? And the way I think about this is, lithium ion batteries in EVs can probably do, I'm gonna throw you a number, and you're the expert that can tell me whether I'm right or wrong, is around about 1,000 charge cycles before it gets to its 80% or so, which then in my Jaguar I-Pace means that I would have done around 350 to 400,000 kilometers in that EV. So again, is the degradation of lithium-ion batteries in an EV really that bad? Have we reached a point where it's not risky to drive an EV because the battery might just outlast the car?
Absolutely. So I would say no, it's not that bad, because your approximation of how long your battery would last and how far you could go, you are pretty much able to use the battery for as long as you would be using a typical vehicle. So we focus a lot on degradation of the lithium-ion battery because we're trying to get it to last even longer. But I think that this anxiety related with having only a certain amount available from your battery for a certain amount of time, I think that people could be a little bit more, your general public could be a little bit more educated in this aspect, because as you say, you can typically go about 1,000 cycles, or if not more, and that is, you're going quite, giving the car quite a range, which when you're buying your typical vehicle, and just a typical internal combustion engine vehicle, I don't imagine that people tend to keep their cars for much longer than 300,000 kilometers anyway. So
exactly.
Yeah, you make a really good point, and completely, I do agree with you there. I think that the degradation of the battery is sometimes overemphasized, but we're looking at it because we want the batteries to last even longer. We're not trying to create this anxiety around the fact that the battery is constantly degrading. Your vehicle is also constantly degrading, and everything in terms of environmental effects and such.
Well, I mean, we might have a battery that could last 1 million kilometers, but then you might be sitting on the floorboards of the car.
Exactly, 100%.
So last question from me, Francis, and then I'll let you go, because it's it's been so fascinating. Is and you might or might not have done some reading in this area. Is there life after lithium ion?
Yeah, that is a very interesting question. I can't answer you too accurately, because my life currently is lithium ion. So that's where a lot of the focus of the research still is. I think that there's a lot of work being done in a lot of interesting other aspects of battery applications, and I firmly believe that researchers can, if they find something better or that can contribute even better, I'm sure that they will within due time. But I think we are very much stuck on lithium ion for the next little while.
Stuck on lithium ion.
Stuck on lithium. There we go. Well, I think that's what we're gonna close with the morning session of day one. Francis, thank you so very, very much for your time and sharing those studies with us. I think it's people like you who are going to help the average consumer like myself understand what I'm going into and be able to counter all these naysayers and people who throw stuff at you. People like you who can give us the facts. The couch experts. Couch experts from everything from a conflict in Europe to whatever else. They're everyone. So we know that, and with people like you giving us the real information, I feel that it gives us the opportunity to make educated decisions. So thank you very, very much for your time.